All right, welcome to the Explainer. Today, we're going to pull back the curtain on something you use every single second you're online, but probably never think about. It's the invisible engine that powers, well, everything, a protocol suite called TCP/IP. And trust me, it's the real unsung hero of our digital world.
So have you ever stopped to think about this? How is it possible that you can be streaming a movie, sending an email, and downloading a massive file all at the exact same time, and it all just works flawlessly? It really does feel like magic, doesn't it? But it's not magic. It's just some seriously incredible engineering.
Well, the secret behind all of that multitasking is a set of rules, a protocol that was designed over 50 years ago. Can you believe that? The foundation for our modern internet was laid down way back in the 70s. It's this invisible engine that's been running in the background this whole time.
Okay, so let's get into it. To really appreciate just how brilliant TCP/IP is, we have to travel back in time. We need to understand the problem they were facing before the internet even existed. What was the challenge they were trying to solve?
So picture this. It's the early 1970s. There isn't one big internet. Instead, you've got a bunch of separate, totally different networks. You had the famous ARPANET, sure, but then there were also these new satellite networks and even packet radio networks popping up. And the huge problem? None of them could talk to each other. They were basically digital islands. So a couple of guys, Vint Cerf and Bob Kahn, set out to build the bridges between them.
See, the protocol they were using at the time, something called NCP, just wasn't going to cut it. It was built for one single happy family of computers on the ARPANET. It never imagined having to connect completely different types of networks with different hardware. I mean, how do you get a satellite network to play nice with a packet radio network on the ground? It was impossible. What they needed was a universal language, a standard that could tie everything together into a real network of networks.
And the solution they came up with, it was beautiful. It was based on this one core idea that was so simple yet so powerful. It basically turned the whole idea of how a network should work completely on its head.
They called it the end-to-end principle, and honestly, this is the secret sauce of the entire internet. The big idea is this: keep the network itself simple, almost dumb. Its only job is to get data from point A to point B. That's it. All the smart stuff, like checking for errors, putting data back in the right order, all that intelligence lives at the endpoints. So your computer and the server you're talking to do all the heavy lifting. This makes the whole system incredibly robust and flexible.
Now, what's really interesting is that they didn't get it perfect on the first try. The original idea was this one giant, monolithic program that did everything. But then, in 1978, they had this aha moment. They decided to split it into two separate specialized parts. And let me tell you, that decision to make it modular, it was an absolute game changer. And that split created this perfect partnership. You've got the Internet Protocol, or IP. Think of IP as the postal service. Its only job is to slap an address on your data and figure out how to route it. Then you have the Transmission Control Protocol, TCP. TCP is like the certified mail manager. It's the one obsessively tracking every single piece of mail, making sure nothing gets lost, everything arrives in the right order, and nobody tampered with it. A perfect team.
So before any of your actual data, your email, your video stream, goes anywhere, TCP needs to make sure the line is clear and stable. It does this with something called the three-way handshake. It's kind of like a polite digital introduction. First, your computer says SYN. Hey, can we talk? The server responds with SYN-ACK. Yep, I hear you. Let's talk. And then your computer sends one last ACK. Great, I'm ready. Boom, handshake complete. The connection is rock solid, and now the data can start flowing.
Okay, so the connection is open, but how does TCP actually guarantee that everything arrives perfectly? Well, it's got a few tricks up its sleeve. First, every single bit of data gets a sequence number. That way, even if things arrive out of order, the other end knows exactly how to piece it back together. As each piece arrives, the receiver sends back a little confirmation, an ACK. It's like saying, got it. If the sender doesn't get that got it message back in time, it just sends the missing piece again. Simple, right? And finally, a checksum makes sure the data didn't get scrambled along its journey.
All right, so the internet starts to take off. It goes from this tiny little project for academics to a global behemoth. And what happens when something becomes massively successful? It creates new problems. In this case, the internet's own success led to epic digital traffic jams. And here's the wild part. The very first version of TCP, it had absolutely no way to handle traffic jams. None.
The designers, brilliant as they were, just couldn't imagine a future where millions and then billions of people would all be trying to use the network at once. It just goes to show you even the best plans have to evolve.
And that kicked off a whole evolution of TCP. For decades, engineers have been building smarter and smarter traffic cops right into the protocol. We started with early versions like Tahoe and Reno, which were revolutionary for their time. Then came Cubic, which is probably what your computer is using right now, and it's a huge reason why streaming HD video just works. And the innovation hasn't stopped. Now we have things like Google's BBR, which is even smarter, looking at bandwidth and delay instead of just lost packets. It's a constant upgrade.
So that brings us to today. We have this protocol that's, 50 years old. How in the world is it handling the challenges of the modern internet? And what's next for TCP? Well, the biggest challenge it faced in the last couple of decades was almost an extinction-level event for the internet. As billions of devices, smartphones, laptops, smart fridges, you name it, all came online, we were literally running out of internet. The addressing system, the way every device gets a unique number, was hitting a hard wall.
You see, the original system, which we call IPv4, had a limit, a hard limit of about 4.3 billion addresses. Now, back in the 70s, that number sounded practically infinite. I mean, who could possibly need more than 4 billion addresses? Turns out, we could. Today, that's not even enough for every single person to have one, let alone all their devices.
And then, back in 2011, the unthinkable happened. We officially ran out. The central supply of new IPv4 addresses was completely exhausted. Now, engineers are smart, so they came up with some clever band-aids, like a technology called NAT that lets all the devices in your house share one address. But everyone knew this was just kicking the can down the road. We needed a real fix.
And that real fix has a name, IPv6, or Internet Protocol version 6. And it is a monster of an upgrade. It's not just about giving us more addresses, though it certainly does that. It also makes the whole system more efficient, gets rid of all those clunky workarounds, and even builds critical security features right into the foundation.
So how many more addresses are we talking about? Take a look at that number on your screen. That's 340 times undecillion. To put that in perspective, that is more addresses than there are grains of sand on all the beaches of the entire planet. It's a number so ridiculously huge that we will never, ever run out again. Problem solved permanently.
There's this old saying from the early days of the internet that really just nails the spirit of TCP IP, that it'll run over 2 tin cans and a string. And it's so true. That core design philosophy, keep the network simple, keep the endpoints smart, means it's just unbelievably flexible. It doesn't care if it's running on super fast fiber optic cables or, a couple of tin cans. It just works.
So that really leaves us with one final big question. Think about it. This whole system started just to connect a handful of computers for some researchers. Now it connects practically all of humanity. It survived traffic jams, it survived running out of addresses, it's adapted to everything we've thrown at it for 50 years. So you have to ask yourself, what's next? What kind of challenge could possibly be big enough to finally replace this incredible invisible engine of the internet?